Hello, statistics student. This video is for chapter 3.4, part 2. In part 1, we look at how to calculate probability of sampling with replacement versus without replacement. And we figure that if it is sampling, so the main thing is if we're doing sampling with replacement, they are all independent because the population size stays the same. It's easy to calculate. You just keep on multiplying. But we're doing sampling without replacement, which is usually what happened. Then we have to do like the subtraction things like this, the red marble things. Keep on subtracting the top and bottom, which is very clumsy. So, and then we say, well, we could use the 5% guideline if our sample is, if our sample does not affect the probability of the particular features that we are looking at, we can just do multiplication. So this is what happens in this case. If someone gives you a relative frequency and it talks about a very big population, you can safely assume that, oh, this is a big population. We only select 3. It should be less than 5%. So we treat everything as independent. So just keep multiplying. And then we have a special probability that we want to calculate, which is at least one of something, like left-handed, is actually 1 minus the all not left-handed, means all right-handed. So because at least one left-handed is the complement of all right-handed. So to calculate at least one, we can just subtract all right. So I didn't finish this example in the last one. So when I do 1 minus 0.729, the probability is 0.271. Okay. So the main reason why we can do that is, so the steps are here. So it's because they didn't give us the population size. We know, and they only give us a relative frequency for left-handed. So all 3 left-handed can be just written as first left hand, second left hand, third also left hand as 0.1 because probably don't change. Okay. Second example, we have the population size. So this population size is a batch of light bulbs, 6,400 light bulbs, but some of them are defective. So defective is the one that you are trying to find. So you are trying to get some sample to see if there are some defective one, right? So you select 12. So obviously, because there's only 80 of them, so what is the likely size what is the likely probability that all 12, when I say all, that means all 12 are good. That means not defective. So let's find out if the sample size, so see if I can actually do, treat it as independent. So we have to do the sampling proportion. That means compare the one that we pick, all 12, compared to the population, is it small enough? So sample size is 12, population size is 6,400. Divided, that's so much less than 5%. So we would just treat it as independence by applying the 5% guideline. So then the probability that one of them is good is 6,400 minus 80 over 6,400, so it's 0.9875. Probability of selecting one that is defective is 80 over 6,400 is 0.0125. And then all 12 are good would be the good probability, 0.9875, equal to 0.860. So when I do this, I don't round, because if I just do the rounding of 988, I would have a lot of rounding error. So do as much as possible, use the most accurate number. Okay, here to the power 12, because the first is 9875, the second is 9875. Treat them as independent. I can just use the independent rule of keep on multiplying by using an exponent. So that's 0.860. What about probably of at least one is defective? So would be 1 minus all are not defective. That means all are good, right? So that was 1 minus 0.860. That is what? 1 minus 0.860 is 0.14. So that's how you do those sampling probability. Okay, so don't mix up the one that you pick. 12, this is the sample. The 80 is some characteristics of the population that you want to look at. So don't mix them up. The second things I want to do in 3.4 actually does not come from 3.4, is a main use of probability in statistics called the rare event rule. Eventually, we will look at this in I think chapter 9 or chapter 8. So, but I want to go through this one more time. We briefly talked about it in chapter 1 when we used the word significant event, but we would talks about this more because in when we use probability to do inferential statistics, this particular rule is very important. I kind of go through this before in chapter 1, saying that if for statistician, if they see something that is really rare, they will be surprised, and you can actually make some conclusion. So what is it based on? It's based on something called a rare event rule. So the way you do it is you will have an assumption. The assumption is whatever that's is kind of like the um, default or the common assumption or common uh, uh, whatever that's accepted already under this given assumption. Like maybe you take out a coin and then you assume that it's fair, right? You take a dice, you assume it's fair. So under those assumptions, the probability of a particular observed event is very small. Notice, is observed event is not the probability of something that you are going to see. Very often in probability, we are going to calculate something that has not happened. Like you're going to buy lottery tickets. You're going to want to find out what is the probability that you're going to win. You are going to win. That is, you want to estimate your chance. But in probability, we actually see an event that has happened, but we go back and calculate how likely is this going to happen. Now, under the assumption, if the probability of this observed event is very small, and because it's observed, that means you have seen it and it has happened, and the probability that it occur is significantly less than what we typically expect. That means it's so rare that we don't really expect it. Then we come back and say, well, maybe our initial assumption is not correct. Okay, maybe our initial assumption. So the very good example would be you throw a dice. Your common assumption is the dice is fair, but you keep on seeing heads, or you keep on for a dice, you keep on seeing 6 coming up, like all the times. Like maybe you throw it 5 times, you have 5 6. You kind of suspecting that the dice is not fair, right? So you have been very surprised, and you would be questioning your assumption because you've seen it. So this is the kind of the concepts of the rare event rule. Is because of a accepted assumption, and because of that you see a event that's not supposed to happen. So what is being unlikely to happen is by default. Later on in I think in chapter 8 we were able to actually define what is an unlikely event. So if you want to change it to 0.01 or 0.02 or even smaller, you just have to announce it. But by default, uh, 0.05 is unlikely. If A is, after you calculate it, is less than 0.05, that is really unlikely to happen. Now, how do I use this rare event rule to make some conclusion? So the logic is, if I see an event that has happened, but I calculate probability of A is greater than 0.05, A can just happen by chance. I'm just observing something that is normally can happen. So then I would say there is not sufficient evidence to conclude that a change is effective. So you change something out of the acceptable norm, out of the acceptable assumption, and then you see something happen, but actually that event could have just happened by chance, not because of the change. So you would say that's not enough evidence. Whereas if you see an observed event, the chance of it happening is less than or equal to 0.05. It cannot have occurred by chance. It is so rare that you should not have seen it, but it has happened. So you will say that it must be because of the change that makes it happen. So you can conclude that whatever change that make this happen is effective. An example, you want to do a study to see if vitamin C can reduce common cold. 6 out of 56 subjects take vitamin C, catch the common cold, compared to 8 out of 56 subjects not taking vitamin C. So if people don't take vitamin C, the chance of getting a cold is 8 out of 56. For those that takes it is 6 out of 56. So there is the relative frequency is different, right? So this is 6 out of 56. The other is 8 out of 56. Should I just compare the percentage? No. How we don't do that. We don't directly compare the difference. We compare what is the chance of having such a low number. Okay, by common sense, we know that 6 is not too much away from 8. And actually, in probability, we can actually calculate the chance of getting such a smaller number if 8 is the acceptable or the normal range, right? Normally, if no one do take vitamins, if none of the people take vitamin C, 8 out of 56 will catch a cold. So, but it might vary. So sometimes it's 7, sometimes it's 9, sometimes it might vary to 6. What is the chance that it will vary down to 6? The chance is 0.32. And in chapter 5, we'll talk about how to calculate this. The chance of getting such low number is this. What can we conclude? Is 0.32 a rare event? No, 0.32 is not unlikely. It could just have occurred by chance. Sometimes it's 8 people, sometimes you can just have 6 people. So the fact that you have 6 people catch the cold, is it really due to vitamin C treatment? No, it could just have happened by chance. So we conclude that there is not sufficient evidence to conclude vitamin C is effective because it could have just have occurred by chance. So that's the argument. The second example is here. I'm going to do one. A local study shows that 12% of bike accidents have a head injury for biker with helmet, while 25% of biker accidents are head injury for biker who does not wear helmet. So this is a big substantial difference, right? So by common sense, we know that, wow, it reduced from 25% of head injury to 12% of head injury. It must be a big difference. And actually, probability allow us to show that there is 0.01 probability of getting such sample results. Now, you don't calculate this. After chapter 5, you know how to calculate this, and you see that, wow, this is so in general, most of the people is 25%. Sometimes it varies, but it varies up to down to 12% is only 0.10 chance. So we would say the chance of 0.01, the probability of 0.01 shows that the result, can it happen by chance? No. It's so rare that it could not have just occurred by chance. It's possibly, but it's so low. So, but the fact that it has happened, people that wear helmet actually only have 12%. So there is strong evidence to support that the helmet has is the reason for reducing it, not because of chance. Does that make sense? You see something that is usually is 25, but suddenly it becomes 12. The only change is because helmet. So this big change could not have occurred by chance only. The chance you can, if you know probability, you can calculate the chance for a 25% to drop to 12% is 0.01. Cannot have occurred by chance. The only reason you can explain is because of helmet. So it is strong evidence that helmet thus is effective. So this is called rare event rule.